Hey guys, Mr. Ford here. In this video, I'm going to do some more on logic and reasoning, but before doing so, I wanted to take a moment to introduce you to the science of deduction, right? So this is a brief little article, career profile on a gentleman named Mr. Wendell Griffin, and it talks about the power of deductive reasoning and how deductive reasoning is a cornerstone to all of the studies we do today, not just geometry, not just mathematics, but science, language arts, anything, business, everything that you can find in commerce and out there in the real world, we use deductive reasoning. So, deductive reasoning, the cornerstone of mathematical proof, is responsible for a huge portion of the scientific and technological achievements of the past 300 years. But it is equally important in a wide variety of non-mathematical endeavors. Trial lawyers, Wendell Griffin believes that the ability to use deductive reasoning is one of the most useful tools for a trial lawyer can possess. Why? Because a trial is an exercise in reason, he explains. Each side in a dispute has different pieces of the puzzle. When we look at the evidence, we find riddles, and riddles within those riddles. He says, who is at fault? Which witness is more credible? A trial lawyer's job is to construct a model of events so that the judge and jury can reason their way through the logical conclusion. Griffin attended high school in his hometown of Delight, Arkansas, and he earned a degree in political science at the University of Arkansas. After 3 years in the Army, he entered the University of Arkansas Law School, receiving a law degree in 1979. Now a partner in the general litigation department of a Little Rock law firm, Griffin spends most of his time defending employees and workers' compensation cases. In his rare free moments, he enjoys reading. Asked to name his favorite fictional character, he says, without hesitation, Sherlock Holmes. Naturally. So, this is an attorney, a trial lawyer, talking about the importance of deductive reasoning. That's why it's so important to follow along and go through this section that we're going in our textbooks on logic and reasoning. In this video, we're going to introduce the division of segments and angles. So up until this point, we started off constructions, and we mentioned and we studied and we learned how to actually illustrate bisectors, right? Perpendicular bisectors. But we never really got around to going over what those bisectors are, what they mean. I mean, we did study it, we did talk about it a little bit, but never directly did we study just the bisectors, and in particular bisectors of segments and of angles. So, objectives for this lesson. After studying this section, you will be able to identify midpoints and bisectors of segments, identify trisection points and trisectors of segments, identify angle bisectors, and identify angle trisectors. So, part 1, midpoints and bisectors of segments. We shall often work with segments that are divided in half. Definition: a point or segment, ray or line, that divides a segment into two congruent segments, bisects that segment. The bisection point is called the midpoint of the segment. So, notice it's only of segments. We're talking about a point or a segment, ray or line, that divides a segment into two congruent segments. So, divides a segment into two congruent segments, right? So those are bisectors. Only segments have midpoints. Only segments have midpoints. It does not make sense to say that a ray or a line has a midpoint. A ray or a line has a midpoint. It does not make sense to say that because rays and lines go on to infinity. So you can never find the midpoint. You can never find the section that splits it into two equal parts. Remember, midpoint is directly in the middle of the line segment. So notice here, X is not a midpoint, Y is not a midpoint. Why? Because this is a ray and this is a line. Both of those extend on to infinity. In a ray, only one side extends. In a line, both sides extend. So, moving along, how many midpoints does PQ have? How many midpoints does PQ have? This is PQ. Well, there should only be one point that is in the middle of PQ and splits it into two congruent segments. I'm not gonna be very precise here, but let's say this point that I'm drawing, let's say that's the midpoint. If that is the midpoint, then there can only be one midpoint because that would be the precise point where that segment was split into two equal sizes. How many bisectors could PQ have? Well, same thing. You can only have one midpoint. You can only have one bisector, right? Remember that? Bisector splits it into two equal parts. So, study the following examples. Example 1, if line segment XY bisects AC at B, what conclusion can we draw? Well, the only conclusions we can draw is that B is the midpoint of AC and that AB, this segment here, created by that midpoint, is congruent to BC. So, AB is congruent to BC. Example 2, if D is the midpoint of FE, what conclusions can we draw? Well, FD would be congruent to DE, so this would be congruent to this, right? Because it is a midpoint. Point D bisects FE, meaning it splits it into two congruent parts, right? So that would mean that FD would be congruent to DE. And DG bisects FE. So notice they're giving you first a point that bisects that segment and a segment itself because this whole segment also bisects that segment. Okay, so that's all that means. It's just giving you another way to write it. And example 3, if line segment OK is congruent to line segment KP, what conclusions can we draw? In this one, if OK is congruent to KP, this is OK here, congruent to KP, then that we can draw that K is the midpoint, right? So that point here at K, let me put height, that is the midpoint. Then JM, that line, this is line JM, notice it goes on for infinity to both sides. Line JM is a bisector of OP, and point K bisects OP. Now, let me zoom in here real quick. Notice this symbol. I know it's kind of hard to see when I was zoomed out, but that, with the little arrow on each side, that means it's a line. Remember that. If it only has one arrow and a point, like this, then it's a ray. A line is going to have an arrow on each side. And then, of course, a line segment is going to have a point on each side, okay? Trisection points and trisecting a segment. So, just going to give you definition here. Trisection points, a segment divided into 3 congruent parts. Here we have 3. Remember that word tri is 3, is said to be trisected, right? Said to be trisected. 2 points or segments, rays or lines that divide a segment into 3 congruent segments trisect the segment. 2 points at which the segment is divided are called the trisection points of the segment, right? So think about this. You have to have at least 2 points. You can't just have 1 point creating a trisection. It's not possible. You have to have 2. So again, only segments have trisection points. Remember, not lines or rays, only segments. And rays lines do not have trisection points, right? Rays and lines go on forever. You cannot have a trisection point. Example number 1. If line segment AR is congruent to RS, is congruent to SC, what conclusions can we draw? So if this line segment is congruent to this line segment, is congruent to this line segment, what can we conclude? All right, that's what it's asking. So let me just highlight. This one's congruent to this one, congruent to that one. Conclusions. R and S are trisection points of AC. Notice R and S, they're given those points of the line segment AC, right? AC is trisected by RS. Those are 2 separate statements. This is the first one, this is the second one. Next example, number 2. If E and F are trisection points of DG, what conclusions can we draw? In this one, we can say that DE, this segment here, is congruent to EF, is congruent to FG, right? So those segments are congruent. And line segment HE, line segment HF are trisectors of DG, okay? So what they're saying is these line segments, they're not saying anything about the relationship of those line segments. They're just saying those line segments are also trisectors of this entire base, okay? Next, we're going to talk about angle bisectors. An angle bisector, an angle like a segment can be bisected, right? Definition. A ray that divides an angle into 2 congruent angles bisects the angles. The dividing ray is called the bisector of the angle. So, you're going to see that you can have a ray that bisects angles, right? For instance, if angle ABD is congruent to angle DBC, then ray BD is the bisector of angle ABC. Notice it says not DB. You have to go from the vertex point when naming it BD, not the other way around. So that line segment BD is correct. Saying line segment DB would be incorrect. If angle NOP is congruent to angle POR and ray OQ bisects angle POR, then ray OP, not PO, right? You're going from the vertex out, is the bisector of angle NOR, and angle 1 is congruent to angle 2, right? So there's a lot being said here. Notice when they write the line segment or they write the ray, they don't do it as PO, they do it as OP, okay? So it's important to note that. Okay, so now we're going to talk about angle trisectors. And angle trisectors are two rays that divide an angle into three equal parts, right? So definition, two rays that divide an angle into three congruent angles trisect the angle. The two dividing rays are called trisectors of the angle, right? And I'm not going to go over much of this because we really don't get into these very often in geometry, at least not in this class. We just have so much other stuff to cover. But I will say this. If we're looking at the examples, if angle ABC is congruent to angle CBD, and angle CBD is congruent to angle DBE, then ray BC and ray BD, let me highlight those, ray BC and ray BD trisect angle ABE, right? So let me zoom in so you can see exactly here. So this is a lot of ifs and then, right? And we're going to get into, in the next lesson, we're going to talk about if-then statements. They're called conditional statements, right? But if triangle ABC is congruent to triangle CBD, right? So that means this one is congruent, let me do another color, to this one, and that middle angle is congruent to this angle, then that tells me that BC, this line segment, or that ray, and BD are trisects, right? They're trisectors of angle ABE, okay? Like I said, we don't deal with this very often in this lower level geometry class, but it is important because you may end up coming across something that tells you or asks you to identify the trisectors, right? Okay, and then the last one, of course, is if, this last example, if ray SV and ray SX are trisectors of angle TSY, then TSV is congruent to VSX is congruent to XSY, right? So one says if those segments or those rays are trisectors, or if those angles are congruent, then those rays are trisectors. And the next one says if those rays are trisectors, then the angles are congruent, right? So that's all it's talking about. Okay, so that's going to be it for this video. We're going to do the sample problems in another video, but I really want to make sure I covered these definitions and vocabulary. As always, I love you guys, and you know what's important. You got to keep shining. Stay golden, my nuggets.